Good everyone. So you're welcome back. Now, last time we dealt with uncontrolled rectifier, right? Uncontrolled rectifier, three-phase. So in that case, we have the 6 diodes, right? Okay, connected just as shown, right? And then from there we were able to see how the output will look like. All right. So now today we are going to look at three-phase control rectifier. Three-phase. So three-phase controlled rectifier. All right. So now remember, when we were dealing with, when I tried to introduce to you about a rectifier as it's converting AC to DC, now we said when you have this like that with a diode, all right, for instance like this, that the output here, output here to the load will look like this. On, off, like that, right? Okay, so now when we talk about controlled, now we are now going to put a thyristor here instead of a diode, so that we can now control this time of on, right? So for us to do that, so I'm going to put a thyristor there, and then I'm going to now introduce firing angle. In other words, I need to know and remember that if there is no signal here, the diode cannot conduct. Right? So it's only when you have a signal in there, then the diode can conduct. So what I'm going to do now is, if I have a signal, let me look at the gate signal, how it will look like, or how this output will look like when I have a firing angle or a gate signal, right? Okay, so here, from here to here is 2 pi, right? And this is pi, this is 2 pi. Now this is pi, so here is pi over 2, right? And maybe here is pi over 4. So if I want this to be fired, all right, at a firing angle of pi over 4, right? So now what I will do is I'm going to come up with a signal that looks like that. All right. So now you see, now what happens is how the system, how this will look like. Remember that this cannot conduct except there's a signal here. So between this 0 point and that point, this cannot conduct. That means that will be out. Supposed to be out, it will not conduct, so it will be 0. All right. So now it will start conducting from here. Let me just sketch it here. So it will start conducting here. So it will chop off this. Now this will now conduct. Right? So if this repeats like that, if the signal repeats, now we have that. Okay. Alright, so in that case, you will get something that will now look like that. Can you see? So you have chopped off some part of this. Okay, at what angle? This is alpha equals to pi over 4 at this angle, right? Of pi over 4. So you get something that looks like that. Okay, so that means if you now have a three-phase rectifier, controlled rectifier, like that, Alright, so if you now have a controlled rectifier, okay, just like as we have it now, you can see it. If you have a controlled rectifier like this, now you can see the output. Alright, so what you see now is the output voltage, how it will look like. Right, but remember, the output voltage will depend on the firing angle. If you have firing angle 0, if you have firing angle being equal to 0, alright, which means here, this is from here, alright, starting from here, like that. In other words, it will still remain now, the output will be exactly like that of diode rectifier when the firing angle is 0, okay, as you can see there, alright, you can see it, okay. Now, if the firing angle happens to change, and you get a firing angle to be, let's say, 30 degrees, 30 degrees, alright, now, this is how the signal will look like. I hope you know what I'm at 30 degrees, alright, so just from here, what is 30? Remember that 90 pi is same thing as 180, right? So pi is 180, so the whole of here is 180, so 30 degrees will be somewhere, alright? So now, once it's 30 degrees, can you see this is how the signal will look like, alright? Okay, the output voltage will look like. And then if you change the firing angle to 60 degrees, this is also how it will look like. Alright? Okay. Now, if the firing angle is 90 degrees, you see how the voltage will be shut off when the firing angle is 90 degrees. Alright? Do you see that? So that's a serious thing. So that means the firing angle will actually determine the nature of the output voltage, and the average value of that DC component will also depend on the firing angle. Okay, so now what you now have here, now is now how the signal will look like when the firing angle is 30 degrees. And then you can see the current, the input AC current, how it will look like. Alright, you see input AC current, that shows that this rectifier is injecting harmonics back to the source. Okay, with input AC current like that, it means it contains a lot of harmonics. Alright, and then also you have the tensor current. Alright. Okay, then if you check out, if you try to derive the DC value for the waveform, for the DC waveform, the way we did for uncontrolled rectifier, alright? Okay, so you are going to get that the VDC, the output voltage DC average value, is the same thing as 1.3505 VLL cos theta. Alright? And also, if you try to get the RMS value, now you are going to get, follow this equation. If you can follow what we did, alright, in the previous video, alright, then you'll be able to get it also. Now you will get that a VRMS value on the DC side is root 2 VLL, okay, by multiplied by the square root of 1 over 2, that is half, plus 3 root 3 over 4 cos 2 alpha. Okay, and then the rest of the equations for average value and RMS currents are the same for uncontrolled rectifier. Alright, so what I'm going to do now is we are going to now look at one question. So let's have a look at one question, and then we'll take it from there. Okay, did you get that? Okay, thank you.